All right, let's look at this next example. Now, this example is going to present us with a slightly different test. Same procedure, but there's going to be one subtle difference that's going to make all the difference in getting this hypothesis test done correctly. So the mean pulse rate of adult males is equal to 69 beats per minute. For a random sample of 15 adult males, the mean pulse rate is 69.6 beats per minute, and the standard deviation is 11.3 beats per minute. Assume the population is normally distributed. Conduct a hypothesis test to decide if the sample statistic is significantly different from the population. All right, so let's start with step one, which is our given information. So let's see here, the mean pulse rate. So we're talking about a mean of adult males is equal to 69. Okay, so we've got the mean pulse rate is equal to 69. This is our original claim. For a random sample of 15 adults, sample size is 15, the mean pulse rate, let me get this here, the mean pulse rate is 69.6. So this mean is in reference to our sample. So our sample mean is 69.6 with a standard deviation of 11.3. Now this standard deviation is still tied to our sample. So this is a sample standard deviation. Assume the population is normally distributed. Conduct a hypothesis test to decide if the sample statistic is significantly different from the population. All right, so one thing that you'll notice that isn't given, do you know what it is? Confidence level. We weren't given a confidence level. So what that means is you can assume that the confidence level is 0.95. And if we've got a confidence level of 0.95, we have a significance level of 0.05. And if we divide that in half, we have 0.025. All right, what else? So the other thing that's missing here is the population standard deviation. This is unknown. We weren't told what this is. So what that implies is that we're going to be dealing with the student's t-distribution now, not a normal distribution. And what's one of the parameters you need for a student's t-distribution? What you need is degrees of freedom, which is sample size minus 1. And so our sample size was 15. So the degrees of freedom is going to be 14, and that's going to come into play later. All right, so you have to pick up on this information in the word problem in order to be able to do a different kind of test on a different distribution. That's the hard part that comes into this. I know you're probably thinking this is all hard, and it is because you haven't done this before. But even when you get the hypothesis test process down, to read a word problem and pick apart all the information that's in it, and then decide what's going to be the right test. Okay, that is difficult too. Okay, so that's all the given and not given information. And that's, going to affect our hypothesis test moving forward. So let's move on now to step 2, which is to set up our null and alternate hypotheses. So here we've got that the population mean is equal to 69. That is our original claim. And the complement of that is not equal to. 69. Okay. Oops, where did everything go? Oh, no. Try this again. Okay, that's equal to 69 and not equal to 69. And the equal to, that was my original claim. All right. So the null hypothesis always has equality. The alternate does not. And this not equal to is telling us that this time we have a two-tailed distribution. Okay, let's move on to step 3. So now we want to calculate our test statistic, okay, which comes from our sample data, and the p-value, which is the area next to the test statistic. So let's go ahead and use the calculator for that. If we were going to do it manually, okay, so now we're going to calculate a t-test statistic, and it uses the formula which looks almost identical, except because we don't have the standard deviation, we have to use the sample standard deviation there. All right, so this would be the formula that we would use. But now instead of using the z-test function, now we're using a t-test function. And I think that's the second item there on the list of functions on the Texas Instruments calculator. So let's see here. This mu naught, that's the value that we're dealing with here. So that's going to be 69 with a sample mean of 69.6, a sample standard deviation of 11.3, sample size of 15, and mu not equal to 69 is our alternate hypothesis. So on the numworks calculator, we're going to have 69 there, and we're going to be choosing this not equal to for the alternate hypothesis. Sample mean of 69.6, standard deviation of 11.3, sample size of 15, and a significance level. Okay, so let's just put in the significance level of 0.05. All right. I wish my computer wouldn't do that. There we go. All right, so let's go ahead and use the calculators. And let me back out of this one altogether. All right, so we want to go to the inference app because that's where our tests and intervals are located. And we back out. Okay, so we want to go to our tests. We're dealing with a single mean, but now instead of a z-test, we want a t-test. And what was this? Mu was 69. And then the alternate is not equal to. All right, so we'll hit next. We're going to input statistics. All right, sample mean of 69.6. Sample standard deviation of 11.3. Sample size of 15. And a significance level of 0.05. Yep. All right. So we'll hit next. All right, and we get our t-test statistic and our p-value, okay, which looks really, really high. And let's leave it at that for right now. Okay, that looks really high. Let's go back. Now we'll go to the Texas Instruments and clear this out. And we'll go to our statistical tests. And the second one down is your t-test. That's what you want to run. All right, so this is 69, sample mean of 69.6, sample standard deviation of 11.3, sample size of 15, and not equal to. Then I'll go to calculate. All right, so it's giving us a t-test statistic of 0.2056 and a p-value of 0.84. Now this p-value of 0.84 is really huge, right? That's really big. But let's use the numworks calculator to show why it's that large. So let me hit next. So what the calculator calculated when we put in a significance level of 0.05 is, since we put in a significance level of 0.05, it's taking that 0.05 area, dividing it in two, and putting 2.5% on this side and 2.5% on that side. So because it's two-tailed, we are also getting a positive two or a positive t-test statistic and a negative t-test statistic. And that was what? Positive 0.206, and then we have a negative 0.206. So if you look at the area to the right, or the area above the positive t-test statistic and the area below the negative t-test statistic, that comes out to an area of about 84%, right? Almost the total area under the curve. That's why 0.84 is so high. Typically, what I do is, typically what you'll see is I'll compare this area to this area, like on the right-hand side, with this area on the right-hand side as well. But I just wanted you to see, kind of how it calculates the area a little bit different, just because it's two-tailed. Okay. And we're going to see that here in the next part of our problem. All right, but let's catch up to where we are here. So we're going to have a t-test statistic of 0.206 and a p-value of 0.840. And so this area of 0.840, that's the area on both sides, or both tails. And so we would think that the p-value is the area in one tail only. Okay, so the p-value on one tail is going to be half of that, or 0.420. All right, so let's move on to the next page. All right, and across the top here, I'm going to say that the t-test statistic is 0.206 and the p-value is 0.420. All right, so let's go ahead and draw our picture. So student seed distribution looks very much the same as a normal. And we're going to have a positive t critical value and a negative t critical value. We know the area in this tail is going to be 0.025, and the area in this tail is 0.025. And the confidence level is 0.95. The region above the tails, this is our reject the null region. And in between, this is our fail to reject the null. All right, what we don't have is we don't have this critical value. Okay, and for that, we need to use inverse t. We need to use an inverse distribution function, so an inverse student's t function. And so I'm gonna put in an area of 0.025 because I'm trying to get this value here only. And the degrees of freedom we calculated on the previous page was 14. There we go. So let's take a look at that. So let me quit out of this function, go to the distribution functions. Now I'll go to inverse t. The area is 0.025 with 14 degrees of freedom. So we get negative 2.144 or negative 2.145. Now it's calculating the area from the left on this one, which is why it's negative. So it's actually going to be a positive 2.145. So let's see here. So we're going to have a positive t critical value of 0. I'm sorry. Not 0. Come on. There we go. Okay. 2.145. So positive 2.145. All right. Now with the numworks calculator, let me back out. I'm going to go to the distributions app. Now we want students t instead of normal. We have 14 degrees of freedom. And I want the area to the right. And we've got an area of 0.025. So we get a positive 2.145. Positive 2.145. Now, like, why am I focusing on just the right-hand side where the critical value is positive? Why aren't I doing it on the left-hand side as well? Well, the reason for that is because our sample test statistic is positive 2, right? And the center of this is going to be 0. So what I can see is that my t-test statistic, which is equal to 0.206, that's going to be somewhere, like right about here. And so if I draw a line up from there, we can see that this is pointing to failing to reject the null, and the area adjacent to it, okay, that could be our p-value. The p-value relative to the area in just one tail, and that was 0.420. So this area is clearly larger than that one, which again is pointing us to failing to reject the null. So the fact that this sample test statistic was positive, that was the reason why I was focusing on this value and not this one over here. All right. So step 5 is because of the t critical value versus the t test statistic and the significance level over 2 versus the p-value. This is telling us that we're going to fail to reject the null, and the null was our original claim. So now we can come down to, oh, are you going to do that to me again? Okay, let me erase that. Okay, the null is our original claim. So here we are failing to reject the null. and the null was the original claim. So this is going to be the outcome we're going to write. So there is not sufficient evidence to support rejection of the claim that, okay, now we put our claim, the mean heart rate of adult males is significantly different from 69 beats per minute and that is with a 95% confidence level. So that is our conclusion. Okay. Given the nature of these values, you might have done a normal distribution and come to the same conclusion. But you really got to be careful with that. That won't always be the case. So, you have to be careful about what you're reading into the word problem at the very beginning and realize, confidence level is not given, therefore I can use 0.95. The population standard deviation is unknown, so therefore I need to use the student's t distribution. And then carry on down with that. And kind of know what statistics functions you need to use along the way. Yeah. Okay. So let's leave it at that. We're done with this think, pair, share, or this example, I'm sorry. Let me know if you have any questions.